All right, so now we're going to get into the graphs. And this first one is going to be an amplitude time graph. And instead of graphing time here, what I've done is I've put t's here. And these t's represent the period of the wave. Let me get nail focus there. The period of the wave. And so just in general in the period, what's going to happen? And I'm going to start our wave at the bottom. So if I took a spring and I pulled it down and then I let go, what if I took this mass here and I pulled it down and let go and it sprang up and down, what would that look like? Well, we're going to start at the bottom at time equals 0. Then we're going to go up, pass through. We're going to make it to the top. And then we'll pass back down. And then, boom, to end, we'll end back where we started. So let's do that one more time. We go up, we pass through the top, come back down, and then end. So here we have two periods, two t's. And the reason I made two of them is so we could get back to this looking wave here. And we have that section right here in the wave. But for our period, let's look. We start at the same spot. So this one to this one, they are the same. So this t is one period. So what are some landmarks here? First is the point of equilibrium. This point of equilibrium is when this line is going to intersect at 0, basically. So in the point of equilibrium on the spring example would be when the mass, if you let it go and it just stayed there, that would be the point of equilibrium, where force gravity is equaling the force provided, the normal force provided by the spring. And then we're going to see that it oscillates. It goes back up to an amplitude, and this amplitude is going to be the same height as the negative amplitude that we pulled it down to. So if it says it pulled it down 10 centimeters, then the top of it is also going to be 10 centimeters, so your amplitude is that 10 centimeters on both sides. Though it looks like it travels a total of 20 centimeters, because if this were 10 and this were 10, the total would be 20. Halfway through the oscillation, you are on the opposite side of the amplitude, or the opposite side of the wave. So one oscillation is not, this is not an oscillation. An oscillation is up and back. For the period, we have to come back. And so when you're at half of the oscillation, you're only halfway. Or if this were a pendulum, it would be, boom, it'd just be on the other side. So now we've got to come back. And this part of the curve right here represents that coming back. So once again, we cross that point of equilibrium, and then we're back where we started. So that's the amplitude graph. This is calculated by the function x equals x of t, t being time, equals the amplitude times the cosine of 2 pi times the frequency times the time. And so that's how we get this graph out of any oscillation. We take our frequency, time is going to be where are we in this oscillation, and then a is your amplitude. So if you're shown an equation and said what's the amplitude, and you see it in this form, you just know that this front number is your amplitude, and you don't really have to do any math. But if you want to know at half a second, and my period is this, what is it? Well, take your period, flip it over, plug in your frequency, and then plug in your time, plug in your amplitude, run it through your calculator, and you will get an x value, which will be the position, or the amplitude, where it is in that wave. So that's the amplitude graph.